In chapter 13 we study rotational motion. Up till now we looked at the motion of objects, the translational motion of objects, translational, and circular motion. And translational motion, of course, was both in one dimension, two-dimensional motion, and circular motion, where an object went around in a circular path, radius r. Now we treated all objects using the particle model, where whether the object was a car, a person, an elephant, didn't matter. We represented the particle with the object rather with a particle. Now in this chapter we're going to look at rigid objects, so an objects which have which occupy a finite volume. So here I have a potato, and we'll look at the rotational motion of rigid objects, where we no longer have the particle model, but we have three-dimensional objects. Actually, three-dimensional objects to deal with. So this is a rigid body, and also look at extended bodies. Extended body. An extended body is where we have a number of particles. So here we have M1, M2, and let's say M3, which are connected to each other via rigid, massless rods. So if we have these rods are rigid and massless, which means that the relative positions of M1 and M2 and M3 remain fixed, while this extended body, let's say, translates or rotates in time. Now, in whether we have a rigid body or an extended body, we need to define the center of mass for the object. For example, the center of mass, let's say, for this extended body on the left hand side might be somewhere in the middle. Now center of mass for the potato might be in the middle here, for example. Now the center of mass is actually the point where that we used to come up with our particle model. We assumed that all the mass of the object was concentrated at one point, and that was the center of mass gave us the means to analyze the motion of an object using the particle model. So what I'd like to do to start chapter 13 off is talk about center of mass and what center of mass is, and how to calculate center of mass for the rigid body or an extended body, in particular the extended body. So first of all, what do we mean by center of mass? Center of mass is the point that describes the translational motion. So if you have an object here, once again I have my potato, the red potato, and if the center of mass is where I put the X mark, and if the potato is translating to the right, then I can represent the translational motion of the potato by using our familiar particle model, which shows the translation of the particle, the translational motion of the object to, in this case. Now, also, furthermore, the center of mass is the point where an object balances if picked. So if we have, rather than a potato, let's say a simpler example is a pencil. If you take your pencil and let's draw a pencil here with a eraser at the top. So if you take your pencil, the center of mass is, we might correctly guess, is somewhere in the middle. You can pick your pencil, you can balance the pencil with your finger at the by balancing at the center of mass. So center of mass is the point where you can balance an object if by picking it right there. And furthermore, center of mass is a point where the force due to gravity or weight seems to act at. So if the center of mass of the object that I have up here, let's say for the sake of argument the center of mass is where I put the X mark, then the force of gravity on this object at the top seems to act at center of mass. Now we know that the force of gravity acts all over the object, but for calculation purposes, for mathematical purposes, we can you can actually show that it seems as if all the force due to gravity seems to act at a single point, which is the center of mass of the object. Now, how do we go about calculating the center of mass in the case of an extended body? Well, if here I have an extended body, it is made up of 4 discrete objects, which are whose masses are 1m, where m is the unit of mass. So it could be a kilogram, 2 kilogram, 10 kilogram each, whatever. So we have 1m, another 1m up here, a 3m mass, and a 2m mass at the lower right hand corner. And each mass is positioned at one corner of a square of side L. It's the square of side L. Now, center of mass is the average position of objects weighted by mass. So the average position of object weighted by mass, which mathematically is given by this function right there. So what the first thing that one needs to do is to come up with a suitable xy coordinate system. After all, we're interested in defining the center of mass in terms of an x coordinate and a y coordinate, because we need to fix it in space. We need to find the position of center of mass. A suitable xy coordinate is one where you make sure that as many of the objects, these discrete objects, lie on one or the other coordinate as possible. That will simplify your arithmetic. You don't have to go with that. You can draw your xy coordinates in any which way, in any position you like. However, it behooves you, in order to simplify the math, to make sure that you draw the xy coordinates, which of course have to be perpendicular to each other, in such a way that as many of the objects lie on one or the other coordinate as possible. As you can see here, I have made sure that at least well, 3 of the masses are on one or the other coordinate. Now, having done that, then go ahead and write the coordinates for each mass. The coordinate for the 3m mass, the red one, is 0, 0. That's at the origin. The 2m mass is L0, where L is the x coordinate. The 1m at the top here is LL, and the 1m here is 0L. Having written the coordinates for each mass, then the x coordinate for center of mass is given by this mathematical function here, which is the sum of each mass multiplied by its x coordinate, divided by the sum of all the masses. So you go around one by one. Let's take the 3m mass first. The 3m mass multiplied by its x-coordinates is 3 times 0, or 3m0, which is this term right here. Then the next mass is 2m multiplied by its x-coordinate, which is 2ml. Third mass is the 1m multiplied by its x-coordinate, which is 1ml. And finally we have 1m multiplied by its x-coordinate, which is 1m times 0, divided by the sum of all the masses, which is 3m plus 2m plus 1m plus 1m, which is equal to, at the bottom we have 7m, and at the top we have 2ml plus 1ml, which is 3ml, which gives us 3 over 7l as the x-coordinate for center of mass. Now for the y-coordinate of center of mass you do a similar exercise. So the y-coordinate of center of mass is given by this expression right here, which is the sum of the product of each mass with its y-coordinate divided by sum of all the masses. So once again you go around and multiply each mass by its y-coordinate, right? And if you do the math, you have 2ml divided by 7m. Therefore the y-coordinate, the y-coordinate of center of mass is equal to 2 over 7l. So our center of mass has coordinates of 3 over 7l and 2 over 7l, which puts the center of mass roughly here, I guess. So this is the center of mass for this extended body, which means that if we were to draw the weight vector acting on this extended body, it would be a vector right there. So this is where the weight would be acting. The force due to gravity would seem to act on this extended body. So if we were to pivot this object at this red point here that I'm drawing at where the mass 3m is, you would expect this extended body to rotate clockwise due to force of gravity, of course. So the expressions to utilize to calculate the center of mass for an extended body are rewritten here, and if you make sure that you draw a suitable XY coordinate system first, write out the coordinates, the XY coordinates for each mass, and then simply follow these expressions to calculate the center of mass. So let us now do a quick example where, let's say, our extended object is a 1 kilogram mass connected to yet another 1 kilogram mass connected to yet another 1 kilogram mass. And actually the way I draw it is not a very good drawing, so let me redraw this. Let's make this an equilateral triangle. 1 kilogram mass, side L. Okay, if it's side L, then a suitable XY coordinate system would of course be something like this, perhaps, where I have at least two of my masses on one of the coordinates. So if it's an equilateral triangle where each side is L, then I know, well, let's go ahead and write the coordinates for each mass. So I have 0, 0 here, we have L, 0 there, and this fella right there, well, let's think about that a little bit. We have an equilateral triangle, so so interested in finding this height right there. This is 60 degrees in an equilateral triangle. Therefore, this side here, which we'll call H is equal to L sine theta, or sine 60 degrees. Okay, so that's the x coordinate. I'm sorry, that's the y coordinate of the 1 kilogram mass at the top. So that's L sine 60 degrees. And as far as the the x coordinate, once again, if that's 60, then this is 30 degrees here. So we have, if we call this distance there h, say this is h1, this is h2. H2 is L times sine of 30 degrees. So this would be L sine of 30 degrees. So using geometry, you need to come up with the x and the y coordinates for each mass involved. Then go ahead and use the expression, the x coordinate of center of mass is the sum of each mass multiplied by its x coordinate divided by the sum of the masses, and the y coordinate of center of mass is the sum of each mass multiplied by its y coordinate divided by sum of sum of all the masses. Now let me bring my calculator out so I can. So for the x coordinate center of mass, we have the first mass is 1 kilogram times 0, so that's the 0 term. Second mass is 1 times L, so 1 times L. And the third mass is 1 times L sine of 30 degrees, which is a half, so that's 1 times a half, divided by sum of all the masses, which is 3. So the x coordinate becomes 1. There's an L there, 1.5 L over 3. Yes, which is 1/2 of L. So half a L is where the center of mass is, the x coordinate of the center of mass is. And as far as the y coordinate goes, if we do the math, we end up with 0 from multiplying the first mass with its y coordinate, 0 from multiplying the second mass with its y coordinate. That's why I said it's helpful to make sure as many of the masses fall on one or the other axis. And for the third mass, we have 1 kilogram times sine of 60 degrees, so that's 0.87 L divided by sum of all the masses, which is 3. So we end up with roughly 0.3 L for the y coordinate of the center of mass. Therefore, the y coordinate of the center of mass is, well, the coordinates for the center of mass are half an L and 0.3 L, which puts us somewhere along half an L and 0.3 L, somewhere here. So that's where the center of mass for this extended object would be. Okay, right where the x is.